In this video, we're going to be starting Chapter 8 and learning about momentum and momentum conservation. So we already talked about energy conservation, and momentum and energy kind of go hand in hand. These are two things that physicists really strongly think are conserved across the universe. So energy can't be created or destroyed. It has to end up in some different form. And the same goes for this new quantity we're about to learn about, momentum. So momentum, also something that is strictly conserved. Sometimes maybe it's hiding, but we can be assured that it goes somewhere in a problem, and we can use this to figure out what's going on in lots of cases. So we'll start by defining momentum. So for our variable momentum, we use a lowercase p. Don't ask why. And our momentum is very simply defined. It is equal to mass times velocity. So if we have an object with some mass moving at some velocity, its momentum is just the product of those two. So our momentum is a vector, meaning that this is something different than energy, right? For the kinetic energy of an object, 1/2 mv squared, that energy doesn't care what direction the object is going. If it's going to the right or to the left or up or whatever, the kinetic energy only cares about the speed, like how fast it's going, not what direction it's going in. Our momentum is a vector, which means that our momentum has a direction and a magnitude, meaning that an object with momentum going to the right is going to be treated very differently than an object with momentum going to the left, even if those momentums are the same size. And we'll get to some examples of that momentarily. But this is the important part. So our units of momentum are units of mass times units of velocity. That is kilogram meters per second. Sometimes it's written as that. This is also equal to newtons times seconds. And you see this one mostly in physics classes. You see Newton seconds more in engineering, these sorts of fields. It really doesn't matter. We'll just use kilograms times meters per second because that's easy enough for us. It does not have its own special name. There's no special momentum unit. It is just m times v. So that's what we get. All right. Now, our momentum, because it's this vector quantity, this equation has to be true in any direction, as we've seen with other vector equations. So what that means is this equation has to be true in the x direction. So in other words, we can talk about the components of momentum. So if I have an object moving with a velocity in the x direction, its momentum has an x component that is equal to mass times that. And of course, we get the same equation in the y direction. So these are the two directions of our momentum definition equation. And remember, our x and y components of our velocity could be positive or they could be negative, right? So if I have an object going up and to the right, here, Vx is positive, here, Vy is positive. So both of these would be positive, and so both Px and Py would also be positive. But I could just as easily have an object moving up and to the left, where Vx is negative and Vy is positive. So now I have a Px that is less than 0, right? Vx is to the left, so that's negative. So I have a negative amount of x momentum, but a positive amount of y momentum because Vy is positive. So that's something we'll have to keep track of with momentum, whether our momentum components are positive or negative. And that's just the same as what we've done with velocity and forces up to this point. All right. So we'll erase this. So if I have a system that's made up of multiple objects, the total momentum is like the sum of all the individual momentum pieces, right? So the total momentum of the system is the sum of all the individual momentums, which is like, you know, the momentum of object 1 plus the momentum of object 2 plus all the other momentums. And just like our other vector equations, this also has to be true in the x and y directions. So our x components have to add up to give the total x momentum, and the same thing in the y direction. The total y momentum is the sum of all of the y components, which is p1y plus p2y plus so on and so forth. Okay, so this is useful because momentum is going to be particularly useful for looking at multiple equations undergoing some interactions. Okay, let's do a very brief example here. We'll erase this. So let's imagine that we have a system consisting of 2 balls, and we'll say these are 2 kilogram balls. And this one's going to the right at 3 meters per second, and this one's going to the right at 5 meters per second. So what is the total momentum of this system? I guess I should label these 1 and 2. So object 1, and this is all just in the x direction, right? Everything's happening in one left-right axis direction, so this is just a one-dimensional problem. We don't have to worry about components, or we don't have to worry about components in the y direction or whatever. So our momentum for object 1 is equal to mv, so that's 2 times 3, so that is 6 kilogram meters per second. The momentum of object 2 is mv, 2 times 5, so that's 10 kilogram meters per second. So the total momentum, the sum of all of our momentums, is 10 plus 6 is 16 kilogram meters per second. This is, this is as easy as it looks. We're just adding up these two values of the momentum to give us a total momentum. Now, and here's why I wanted to do this example. Let's say that we change our picture. So we still have the same balls, and they still even have the same velocity, they still have the same speeds, but we've changed the direction of ball number 2. So this one is still plus 6 kilogram meters per second, but this one is minus 10 kilogram meters per second, not plus 10. So now, when we add these together, we get plus 6 minus 10, which is minus 4 kilogram meters per second. So we change what direction this ball is going, and we change the total momentum of the system. Now contrast that with kinetic energy. Now I didn't prep numbers on this, but I guess we can do it really quick. If we were thinking about this in terms of kinetic energy, 1/2 times m times v squared, that gives me, this one has 9 joules of kinetic energy. This one has 1/2 mv squared. This one has 25 joules of kinetic energy. So the total kinetic energy is equal to 9 plus 25, which is 34 joules, right? And when we change the direction of ball number 2, this does not change. Like, both of our kinetic energies stay positive no matter what direction these velocity vectors are pointing. So this number stays the same even when we change this direction. And so that is one example of the difference between momentum and energy, and really, why it's important, why the momentum cares about what direction things are going in, because that totally affects the numbers that you get from that. Okay, so let's talk about conservation. This is just a numbers example. This is not, I just wanted to show you, how to calculate stuff. This still probably doesn't make a ton of sense conceptually. So let's talk about conservation. So in order to talk about momentum, let's step back and talk about energy conservation just for a second. So remember, our mechanical energy was conserved if there were no non-conservative forces, meaning no friction-like forces. So as long as we had a frictionless surface, we could let the roller coaster car go from the top and figure out what its velocity is at any point on the roller coaster track, as long as we knew the height and how fast it was going at the top, right? If we know how much energy we started with, we know how much energy there has to be at any subsequent point. And there being no non-conservative forces was the important thing here. If there's friction, then we're losing energy, and we don't necessarily know how much, so we can't apply this law anymore. Okay, so our equation for this, sorry, this said friction-like. Our equation for this conservation was that our final energy was equal to the initial energy, or really, U final plus K final was equal to U initial plus K initial, right? We can split up energy into potential and kinetic, but they have to add up to the same total. Okay, that's energy. For momentum, our momentum conservation is slightly different in a way that turns out to be very useful. Our momentum is conserved if there are no net external forces. And this phrase should look familiar. This is the same as from our statement of Newton's first law, objects in motion, objects at rest, unless acted on by a net external force. So what's cool about our momentum conservation is this is still conserved even if we do have friction-like non-conservative forces, as long as those are not external. In other words, as long as those are internal forces. And I'll show you what that means in a little bit. Our equation for this momentum conservation is the sum of all of our initial momentums is equal to the sum of all of our final momentums, where we're summing over all of the different parts of our systems. This is the total momentum at the beginning and the total momentum at the end, and we're treating these like vectors. So, we could write this as the sum of Pix equals the sum of Pfx. So the total x momentum has to equal the final x momentum, and the initial total y momentum has to equal the final total y momentum. So that's, that's our two equations that we get out of our one vector equation. Okay, so yeah, we'll leave that up for a little bit. So our momentum is conserved with friction-y forces as long as they are internal. And what does internal mean here? Well, that means it is not something outside of our system acting on our system. It is something inside our system acting on other parts of our system. So if we're looking at the momentum of two balls, for example, like we just had, they can have friction rubbing against each other as long as they are both parts of our system, because that force is an internal force. It's between two parts of our system. If those balls are rubbing on the ground, well, then that force is external, and we have an external force, and so momentum might not be conserved. So contrast this with our mechanical energy conservation. So here, if there's anywhere energy can be lost, like in these non-conservative forces, that's going to make it so our initial energy does not add up to our amount of final energy. So we can have situations where the amount of energy decreases. We lose energy we lose mechanical energy from our system because of friction-like forces, but momentum is still conserved because these forces are between parts of our system. So, okay, all of this explanation is better served with an example. So we're going to do an example next, and I'll show you exactly what this looks like.